This is the elevator problem for November 7th, lecture number 23. We have an elevator that is 2 meters wide, and part A says, how long does it take for a light pulse to cross the elevator? Well, this is our elevator that's 2 meters wide, and this is our light pulse traveling in this direction with the velocity, and that velocity is equal to 3.0 times 10 to the 8 meters per second for a light beam. And we know that the distance is equal to 2 meters. The time is what we're looking for. Then we have a relationship that says velocity is equal to distance over time by definition. We can rearrange this to be time is now equal to distance divided by velocity. So by making our substitution, we say time is equal to 2 meters divided by 3.0 times 10 to the 8 meters per second, and we plug that into our handy calculator and we get an answer of 6.7 times 10 to the negative 9 seconds is the time it takes for a light beam to cross the elevator. Part B of this problem says, how large an acceleration is necessary to make that pulse deviate by 1 millimeter? Can this effect be observed? So if we take the same pulse of light and we send it across the same elevator, which has a distance of 2 meters, if we accelerate that elevator in the up direction, and if we're watching this from outside this frame, then we should be able to observe the light bend. In this case, what we mean, instead of traveling straight across like it did in part A, now the light would actually travel like this. It would bend as the elevator would accelerate upwards. If this was the case, then we would have this distance of 1 millimeter that we're asking about. So the question is this possible, and what acceleration would that require? Well, let's assume it is possible to start off with. Then we need to find that acceleration. So what we know is that we're going to have a change in y of equal to 1 millimeter. We know that it's going to happen in a time frame from part A of 6.7 times 10 to the negative 9 seconds. We also know that it's going to travel a distance horizontally, delta x, of 2 meters. And we also know that there's going to be an acceleration quantity, which we're looking for, and we also know it has an initial velocity that's all in the x direction of 3.0 times 10 to the 8 meters per second, and it also has an initial y velocity of 0 meters per second. So if that's the case, then we can use our equation that says delta y is equal to v naught y times time plus 1/2 the acceleration in the y direction times time squared. Well, v naught y is 0, so this quantity v naught yt is 0. We know what y is, we know what 1/2 is, and we know t squared, so we solve for acceleration in the y direction. The acceleration in the y direction is 2 delta y divided by time squared. Making our substitutions, we know that the delta y is 1 millimeter, or 1 times 10 to the negative 3rd meters, divided by our time squared, which is 6.7 times 10 to the negative 9 seconds, quantity squared. And again, we plug this into our handy calculator, and we get a value of 4.5 times 10 to the negative 13 meters per second squared. This is a huge acceleration. So that leads us to the last part. Can this effect be observed? Well, the acceleration is so large that no, we can't create this, and so we're not going to see what happens. Part C says, if light is bent by the gravitational pull of an object, then light should fall when traveling parallel to the surface of the Earth. How far does a beam of light travel in 0.001 seconds, and how much does it fall over this distance? Okay, well, so the first thing we want to know is exactly how far is a beam of light going to travel during this time frame. So again, we go back to our initial idea that velocity is equal to distance divided by time. We can rearrange this equation to say d is equal to velocity times time. Okay, well, if that's the case, then we can just say that d is equal to our velocity of light, which we know is 3.0 times 10 to the 8 meters per second, times time. In this case, time's given to us to be 0.001 seconds. And so we get a distance of approximately 3 times 10 to the 5th meters. Get this distance of 3 times 10 to the 5th meters. So this is the same distance over which gravity is actually going to operate on the light beam, causing it to come down. So if the light beam's traveling over the surface of the Earth, say in this direction, and the Earth is here, then if this is the case, then the gravitational pull would be operating on the light in this direction, we can call it force of gravity, then it would cause it to bend. So the question is, how much would that occur? Well, we go back to the same solution we had on part B, and we start off with the equation delta y is v naught yt plus 1/2 ayt squared. Well, again, we know the initial velocity in the y direction is 0 because the light beam is traveling horizontally to the surface of the Earth. So if the initial velocity in the y direction is 0, we're solving for delta y. Delta y is equal to 1/2. The acceleration in the y direction in this case is due to gravity, so it's 9.8 meters per second squared. And its time to value of time squared, again, time was given to us to be 0.001 seconds squared. And so, again, if we slap all this into our handy calculator, we get a value of something roughly like 4.9 times 10 to the negative 6 meters. Well, let's ask ourselves something. Is this feasibly possible to even measure? Well, let's look at this. Over a distance of roughly 300,000 meters or 300 kilometers, all right, we travel in the x direction. We have a displacement in the y direction of roughly, well, it's 0.000001234549 meters. And again, this is in the negative y direction. So if we take a look at this, I mean, the answer is no, right? You couldn't measure this. This is so small and such a small scale and happens so quickly that we don't have anything available right now that could physically measure that.